Good afternoon, ladies and gentlemen. My name is Krisztián Kovács, and I have to show my progress since the last progress report. I work at the Department of Orthopedics in Semmelweis University, and my supervisors are György Kocsis and Szilárd Válcsa, and my statistician is Gergely Agócs. My vision is to make brand new custom-made implants and designs by updated understanding of bone behavior, and my mission is as part of an orthopedics team. We are providing cutting-edge orthopedic service based on evidence-based medicine and research. We have two ongoing projects. The first is dealing with the elasticity of bone, and the second is dealing with the surgical therapy of chronic acromioclavicular instability. My first project is a systematic review and meta-analysis, and this is where we are standing right now with this project. Since the last progress report, after the data extraction, we have done with the risk of bias assessment, and during the statistical analysis, we have realized that this project and the mathematical equations are more difficult than we first thought. Therefore, we had to reassess the whole table with 120 articles from one new aspect to be good enough for the proper mathematical equation, for the new mathematical equation. And unfortunately, due to its difficulty, it takes time. Next to it, parallelly, we started the manuscript writing, so we are done with the supplementary material. We started the methods and the introduction part, and we have done with the cover letter part. But as I mentioned before, we are still waiting for the results by the statistician. During the risk of bias assessment, there was no article that we needed to exclude, and we are done with the journal selection as well from the first top 5 journals. Our primary target is the Acta Biomaterialia, and we are writing it with waiting for the final results. The background of this project, the elasticity, the young modulus or the elasticity of bone. In order to achieve better implant fitting, finite element analysis requires precise young modulus results. However, in the literature, these values are controversial. There are several methods to measure the young modulus. There are macro and micro mechanical testings, ultrasonic and non-indentational testings as well. On this slide, you can see several young modulus values. However, as you can see that there are sometimes order of magnitude differences even taken from the same place, but from different authors. And this is a problem if you want to make a good finite element analysis. The aim of this project is to categorize the different factors and compare the corresponding young modulus results. On this slide you can see our PICO, and according to it, we conducted our search. In this search, we were looking for young modulus values that were from only human bones and only from experimental tests. So the ones that were from MRI or CT values, they were not accepted, only experimental ones. Following this PICO, we conducted a search on this date from these databases with this search key, and we from the first search records of 21,000, we decreased the number to 120, from which the table were made. And these are the preliminary results, because as I mentioned before, we are still waiting for the final ones. We've done from 120 articles from 22 countries, and the ratio of the methodology can be seen on this pie chart, and the ratio of the cancers and the cortical bones are almost equal. If we look at the origin of the samples, bone samples, the top three were the femur, tibia, and the vertebra. and we were distinguishing the epi, metal, and diaphytic regions of the bones. But we must not forget that the bone has an anisotropic feature. It means that if we take a sample, a bone sample, it will have 3 different elasticity value according to the loading axis. So we will have AP, axial, and side loading values for the same sample of bone. From the articles, or in the articles, there were single sample values and multiple sample values as well. And now I'm showing the single sample values of axially loaded experiments. On this slide, we were distinguishing, on this slide you can see 2 bar charts from the cortical and the cancellous bone. On the x-axis you can see the value of the Young modulus, and on the epsilon you can see the frequency of the samples itself and their values. In the cortical bones you can see the Gauss curve, and in the cancellous bone you can see 2 population of values. While on the next slide I'm showing the bar charts by the methodology, so the non-indentation and the distractional methodology. They are showing similar Gauss curves. However, if we check the compressional one, then we here again have 2 different population of values. On the scatter plot diagram, you can see on the x-axis the size of the sample, and on the epsilon size axis you can see the value of the Young modulus. With the pink dots or red dots, you can see the cortical bones, and on the with the black dots, you can see the cancellous bone values. What we need to see that among these 2 populations, there are cancellous bone values among the cortical population, and this is a finding that is needed to be further investigated. The strength of this project, that it's invaluable information about 120 articles with extensive and precise detailed data collection. The limitations are the sample Young modulus results, because their axes were very hard to identify from the articles, and there were some missing details in many cases. The conclusion. According to recent data, the cortical bone samples have higher E values compared to the cancellous bone, and another indentation and distractional tests show similar but not identical results to each other. Compressional experiments measure small E values with higher frequencies. The implication for practice is in the custom-made implants and the new implant designs, while in research there is the further investigation in elastic modulus, and it could open new perspectives for the finite element analysis. My second project is dealing with the efficacy of lockdown technique, and we compare it to other surgical techniques used in chronic acromioclavicular instability. This is a retrospective study and systematic review. The acromioclavicular instability is the most common injury of the shoulder girdle. It occurs during high-energy contact sports, and it has a therapy of more than 100 surgical techniques. And our hypothesis that the lockdown technique is superior compared to the other surgical approaches. This is our pickle for this project, where we are comparing the lockdown technique to the other techniques, and the outcomes are the shoulder scores. The clinical implication is the improved treatment in AC instability. This project contains 2 big parts. The first one is a systematic search, which we conducted in April with the search key, and we decreased the first records to 15, and we will do the data extraction from those. And the second part of it is a retrospective cohort study. This is a multi-center cohort study, and we are eager to start it in order to finish the data collection by the end of the summer. Thank you very much, ladies and gentlemen. I'm waiting for your questions, and I think that we have already started to carry away the small stones, so this mountain is already shaking. Thank you very much.
Congrats, fantastic presentations. I just started to wonder after 9 months of listening to your presentation, actually, of course, following very closely your work, that so during implant planning, we will have this data regarding the young moduli. But what about all the other parameters, all the other yes, actual parameters that we will take in consideration when we are planning the implants? How does the young moduli connect actually to other, or are there actually other parameters that we have to consider during planning, and how will they actually connect?
Thank you very much. This is a beautiful question. Actually, during the planning, the young modules is important when we want to check that how will the metal component fit to the bone itself. So what will be the effect between them. However, in order to create or plan properly, you must not forget the shape of the implant and the shape of the bone where you want to implant it. In this case, we find that there were many articles that were creating the planning of the implant from CT 3D CT pictures. However, in those cases, they are using the voxel, and the voxel is not an anisotropic. It don't have the anisotropic feature. It thinks that in every angle that you are using, it has the same value. However, this was the idea where we started that this is not proper for us. We need to find better values in later.
You are doing custom-made implants. In this situation, it would be great if we know the femur or the tibia young moduli. It's just a suggestion to make a custom-made for the custom-made prosthesis.
We plan to use these subgroup analyses as well, but we are not there yet. But yes, we would like to.
Congratulations for your really, you have performed a really huge work. It was not that clear for me during your presentation that you showed us two bar charts. I think it was the young moduli of the cortical bones when you mentioned twice that they have two peaks. Mm-hmm. And why is that? Do you have any ideas about that they are different types of bones, or why can you see it in that case?
Well, this is, as I mentioned on the next chart or diagram, that is some things that we need to further investigate, because we still have only hypotheses, not clear answers at what could be the reason. But I was talking to an engineer who is working at the BME, Budapest Mechanical Engineering University, and he was mentioning that the longer the bone, the more microfracture could be. It means that the longer bone could break more easily than the shorter one in samples. I'm talking about the sample sizes. So the longer could break easily, and maybe this could be an answer. It is not easy to understand for me as well, but he was trying to say it to me or solve this question as well. But I had the same question as you do.
So if I understand correctly, you pulled the young moduli data from the articles and then showed the histogram of them. That's what the bar chart was about.
Yes, but these were only two aspects that we were checking, but there are many other columns in the table. So we are checking the condition of the bone. We are checking that how was it fixated, was it or fixated or not, region, cancerous-cortical. So there are very a lot aspects that we are trying to take into account, but it takes time.
Maybe you can check that you have assessed more than 100 articles, and I don't know if all of them contain this first peak that you can see. So maybe it's just an artifact coming from a small number of articles. So maybe you can check those articles if you can find an explanation.
Yes, and the whole reason of this project is to identify what could be the source of these controversial values. So that's the point of the whole project.